11 minutes. That is not a malfunction. That is not a navigation error. That is not the kind of operational anomaly that a maintenance crew traces back to a faulty sensor board and files in a technical report that nobody reads twice. 11 minutes is how long it takes to listen to 3 songs on the radio. It is how long a college professor takes to explain a concept before opening the floor to questions. It is how long a taxi sits in traffic outside an airport terminal. And on the morning Iran's electronic warfare team executed the most consequential act of technological warfare in the history of unmanned aviation, 11 minutes was all the time it needed to reach inside a $220 million American intelligence aircraft, flying in what its operators believed was uncontested airspace, take hold of the single invisible thread that connected that aircraft to every instruction it had ever been given, and redirect it, gently, precisely, without triggering a single alarm, to a runway inside Iranian territory. Not shot down, landed, intact. The aircraft was the RQ-170 Sentinel, the most classified unmanned surveillance platform in the American inventory. The aircraft that had orbited above Abbottabad on the night Osama bin Laden was killed. The aircraft whose existence the United States Air Force had never officially confirmed, whose capabilities had never been described in any public document, whose radar cross-section and sensor suite represented some of the most closely held technical secrets in the American defense establishment. Iran landed it, took photographs next to it, broadcast those photographs on state television, and invited the world to look. Now, I want you to picture one man. He is the lead engineer of the Islamic Revolutionary Guard Corps' Electronic Warfare Division's GPS countermeasures program, a man who holds a doctorate in signal processing from Sharif University of Technology, Iran's most prestigious technical institution. He has spent 9 years on one problem. Not how to shoot down American aircraft, not how to jam the communications links that connect an unmanned vehicle to its ground station. That problem is well understood. American aircraft are designed to survive it. They are built with encrypted data links, frequency-hopping transmitters, and redundant communication architectures specifically because jamming is the oldest trick in the electronic warfare book. His problem is more specific, more elegant, more dangerous. His problem is this. What happens to an autonomous aircraft when you do not cut its connection to its operators, but instead replace the information that connection is built on? What happens when you do not jam the signal, but change what the signal says? What happens to an aircraft that has been told, by the most trusted, most ubiquitous, most deeply embedded navigation system in the history of warfare, that it is somewhere it is not? On the morning the RQ-170 touched down on an Iranian airfield, that engineer had his answer. Stay with us, because the story of those 11 minutes is not a story about one drone and one landing. It is the story of the weapon that every American precision-guided munition, every cruise missile, every carrier-based strike aircraft, every special operations helicopter depends on, completely, invisibly, and with a trust so deep that the possibility of its failure was never fully priced into the doctrine built around it. And by the end of this video, you will understand why the most dangerous thing Iran did was not take the drone. It was prove that the thread connecting American weapons to their targets could be moved. Not cut, moved. But to understand what Iran built toward that morning, what the 11 minutes represented at the end of a very long chain of deliberate, patient, precisely calibrated investment, we need to go back. We need to understand what Iran has been doing, not in the domain of missiles or drones or surface ships, but in the electromagnetic spectrum itself. in the specific, technically demanding, largely invisible discipline of reaching inside the navigational foundation of American military power and learning to write on it. Because Iran did not develop GPS spoofing in isolation. Iran was shown it was possible. And then Iran spent a decade building the capability to do it at a scale and precision that the American defense establishment had publicly assessed would require resources and technical sophistication that no regional power under comprehensive sanctions could realistically achieve. The technology is called GPS spoofing, and it is distinct from GPS jamming in a way that matters enormously to the people responsible for defending against it. Jamming is loud. Jamming fills the GPS frequency band with noise, overwhelms the legitimate satellite signals, and alerts every receiver in range that something is wrong. The receiver loses its fix. The aircraft loses its position. The pilot or the autopilot knows immediately that the navigation system is compromised. The response, the emergency procedure, the backup navigation mode, all of it activates. Jamming is a blunt instrument. It announces itself. Spoofing is silent. A spoofer generates artificial GPS signals that appear to every receiver within range to be legitimate transmissions from real GPS satellites. The signals carry the right codes, the right timing structure, the right frequency characteristics. The receiver processes them exactly as it would process genuine satellite signals. It produces a position solution. The position solution is wrong. The aircraft or missile or bomb believes it is somewhere it is not. And nothing in the system, not the receiver, not the autopilot, not the flight management system, raises an alert. Because from the system's perspective, everything is working correctly. The navigation data is arriving as expected. The position solution is resolving cleanly. The aircraft is flying toward its target. It is flying toward the coordinates the spoofer told it were its target. Iran's electronic warfare community understood this distinction with a precision that took years of academic and technical work to translate from the theoretical domain of signal processing research into operational hardware. The foundation of that work was not classified intelligence on American GPS receivers. It was mathematics. The GPS signal structure, the pseudo-random codes that each satellite broadcasts, the timing relationships that allow a receiver to triangulate its position from multiple satellites simultaneously are public. The GPS interface control document, the technical specification that defines every parameter of the GPS signal, is a publicly available document. It was published because GPS was designed for civilian use as well as military use. The same signal that guides a cargo ship across the Pacific guides an American JDAM bomb to its target. What the interface control document tells a sufficiently capable signal processing engineer is precisely what a spoofed GPS signal must look like to be accepted as genuine. The codes, the timing, the Doppler shifts that convincingly simulate the motion of satellites in known orbits, the power levels that allow the spoofed signal to gradually overwhelm the legitimate signal without triggering an abrupt transition that a sophisticated receiver might detect. Iran's engineers had the specification. They had the physics, they had the mathematics. What they lacked, initially, was the hardware precision to execute the spoofing waveform with sufficient fidelity at sufficient power across sufficient frequency channels simultaneously. They solved that problem over 9 years, not with resources the United States would recognize as adequate for the task, with the specific, focused, sanctions-constrained resourcefulness that has characterized every Iranian strategic program that Western analysts initially underestimated. They did not need foreign-sourced GPS receiver components they could not import. They needed digital signal processing hardware they could assemble from commercial electronics that did not appear on sanctions control lists. They needed software-defined radio architectures that universities were publishing academic papers about using for exactly the kind of multi-channel signal generation the spoofing waveform required. They needed time. Iran had all three. The GPS spoofing system that the IRGC Electronic Warfare Division deployed operationally in 2011 was not, by the assessment of Western analysts who examined the RQ-170 incident in the years following, a system of exceptional technological elegance. It was functional. It was precise enough. It was precisely what the mission required, and nothing more. The RQ-170 was not flying in a highly dynamic combat environment, where its autopilot was executing rapid altitude changes and sharp course corrections that a spoofed position solution would have struggled to accommodate without triggering attitude warnings. It was flying a gradual surveillance orbit at relatively constant altitude and airspeed, the kind of flight profile that gives a spoofing system the maximum time to establish its false position baseline and the maximum tolerance for the errors that even a good spoofing signal introduces. The spoofer did not replace the drone's GPS position instantly. That would have triggered alarms. It moved the position gradually, a drift, a few meters per second in the direction of the Iranian airfield the IRGC had designated as the recovery site. The autopilot accepted the drift. The flight management system updated its position estimate. The aircraft followed its autopilot instructions toward what it believed was its programmed course. The course was taking it toward Iran. The engineers watched their screens and waited. 11 minutes after the spoofing signal achieved the position dominance that allowed the gradual redirect to begin in earnest, the RQ-170 descended toward the airfield its navigation system told it was the friendly base in Afghanistan it had departed from. It touched down. It was intact. Here is the military reality that no Air Force procurement review has ever stated in public. Every precision-guided weapon the United States military fires relies on GPS, not as one of several navigation options, as the primary navigation source for the guidance systems that have redefined American military power since the Gulf War of 1991. The JDAM, the Joint Direct Attack Munition, the guidance kit that converts a standard unguided bomb into a precision weapon, navigates using GPS. The JASM, the Joint Air-to-Surface Standoff Missile, the long-range cruise missile that American aircraft launch from outside enemy air defenses, GPS. The Tomahawk cruise missile, the signature weapon of American naval power projection, the missile that has opened every American air campaign since 1991. GPS, combined with terrain-following radar and inertial guidance, but GPS as the primary precision reference. The navigation systems of every American military aircraft, from the F-35 to the B-2 to the MH-60 helicopter that carried the SEAL team to Abbottabad. GPS, the precision that allows American artillery to fire a shell onto a specific building from 30 kilometers away. GPS, the entire American way of war, the doctrine of precision strike, of minimal collateral damage, of achieving military objectives with smaller forces and fewer weapons than any previous era of warfare required, rests on the assumption that GPS works. That when an American weapon is told where its target is, the information that takes it to that target is accurate. That the invisible thread connecting the weapon to its objective is real. Iran spent 9 years learning to make that thread say something different. Dr. Todd Humphreys of the University of Texas at Austin, the researcher whose team first demonstrated practical GPS spoofing attacks against civil receivers in 2012, and who has published the most rigorous public assessments of GPS vulnerability to spoofing attacks, stated in a congressional testimony that the assumption that military GPS receivers are immune to spoofing because they use encrypted signals, the P-code and M-code signals that civilian receivers cannot access, was never fully tested against the specific attack surface that the RQ-170 incident exposed. His assessment was this: military GPS receivers are more resistant to naive spoofing than civilian receivers. They are not immune to spoofing by a sufficiently capable adversary who has characterized the signal architecture carefully. And careful characterization of a signal architecture does not require access to classified information. It requires access to physics. Physics, not classified documents, not stolen technical manuals. Physics. The same physics that Iran's engineers had been applying to the GPS interface control document for 9 years was available to them without stealing anything. They needed to understand how the satellite geometry produces the receiver's position solution. They needed to characterize the error tolerances that the receiver's filtering algorithms would accept before flagging an inconsistency. They needed to know how fast they could move the false position without triggering the receiver's integrity monitoring. All of that is a problem in applied mathematics, not intelligence collection. Here is what American state channels will never fully show you. In the weeks following the RQ-170 recovery, the American intelligence community conducted an assessment of the incident that was classified at a level that placed most of its findings beyond the reach of the congressional oversight committees, with nominal authority over the programs the assessment addressed. The unclassified summary that reached broader circulation described the incident as an anomaly attributable to a combination of communications disruption and navigation system failure. The classified assessment described something different. The classified assessment described the first operational demonstration by any adversary of GPS navigation spoofing against a military-grade autonomous aircraft under real operational conditions. That description had implications that the classified assessment then traced through the entire inventory of GPS-dependent American weapon systems, not theoretically, with specific reference to the signal processing architectures of specific guidance kits. The implications produced a classified list of vulnerability assessments that the defense procurement offices for each affected system were required to address in their next acquisition cycle. The acquisition cycles continued. Some of the vulnerabilities were addressed in upgraded guidance kit variants. Some were acknowledged in program documentation and deferred to future upgrades that have not been fully funded. Some were acknowledged and retained as acceptable risks, given the cost of redesign. The RQ-170 was recovered intact. Its sensor payload, the most sophisticated airborne intelligence collection suite ever lost to a hostile power, was documented, photographed, and shared with Chinese and Russian technical teams, who arrived in Tehran within weeks of the recovery. Not because Iran had a strategic relationship with China and Russia that required such sharing, because Iran had something China and Russia both wanted to examine. The sensor architecture of the most capable unmanned surveillance aircraft in American service, intact, unburned, on a table in a facility where foreign technical teams could spend days with it. What Iran gave China and Russia that week cannot be fully assessed from open sources. What can be assessed is that every American unmanned system deployed in the Gulf, in the Pacific, and over contested airspace in the years following the RQ-170 incident was flying against an adversary technical community that had spent days examining the physical architecture of the system that American planners relied on to collect the intelligence those systems were supposed to provide. The vulnerability was not just in the navigation system. The lesson was that the navigation system was the entry point to everything else. In the years following the RQ-170 incident, something shifted across American military operations in the Gulf and beyond that no press conference described, but that every commander who relied on GPS-guided weapons in contested environments processed with full seriousness. The United States military invested significantly in GPS anti-jam capabilities for its guidance systems, hardened receivers that could maintain lock under active jamming conditions. The investment was real. It addressed jamming. It addressed the blunt instrument. The spoofing problem, the silent instrument, the instrument that does not jam the signal but changes what it says, received attention in classified research programs whose progress has not been publicly described in the same operational terms as the anti-jam investment. Lockheed Martin's GPS Solutions division began receiving accelerated research contracts in 2013, for what the company described in public securities filings as enhanced signal authentication architectures for military GPS receivers. Signal authentication is the technical solution to spoofing. If the receiver can verify that the signals it is receiving are genuinely from the satellites they claim to be from, a spoofed signal is rejected. The technical challenge is that authentication requires the receiver to process additional information that the current GPS signal architecture does not include in its basic structure. Adding that information requires either a new signal standard that would require updating satellites already in orbit, or a ground-based authentication system that generates the verification data the receiver needs through a separate channel. Neither approach is simple. Neither approach is cheap. Both approaches have been in development in some form since 2013. They have not reached full operational deployment across the entire inventory of GPS-guided American weapons as of the last publicly available program review that addressed the issue. Iran did not demonstrate GPS spoofing once and stop. Between 2011 and the present, Iranian GPS spoofing operations have been documented or credibly assessed in the shipping lanes of the Persian Gulf, where commercial tankers operating under GPS navigation have reported position anomalies consistent with spoofing. In the airspace over Syria, where Iranian-affiliated electronic warfare systems deployed with Russian technical assistance have produced documented navigation disruptions affecting commercial and military aircraft. And over Iranian territory itself, where successive generations of the GPS countermeasures program have been tested against the kinds of unmanned platforms that American operations in the region continue to rely upon. Each operation produced data. Data on receiver response times. Data on the drift rates that different autopilot systems would accept before triggering anomaly flags. Data on the relationship between spoofing signal power and the time required to establish position dominance over the legitimate satellite signals. Data that the IRGC Electronic Warfare Division's engineers have used to refine the spoofing waveform through multiple generations, each more precise, more adaptable, and more capable of addressing the specific signal processing architectures of the updated GPS receivers that American procurement programs have deployed in the years since 2011. The 11 minutes in 2011 were not a lucky shot. They were the proof of concept for a capability that Iran has been improving with the systematic patience of an organization that understands it cannot match American precision weapons production, but can invest in understanding the electromagnetic foundation that precision weapons production depends on. Could Iran today spoof a JDAM guidance kit? Could it redirect a Tomahawk cruise missile? Could it deliver an incorrect position reference to the navigation system of an F-35 operating over Iranian territory, causing the aircraft to believe it is flying a course it is not flying? These are the questions that the classified vulnerability assessments commissioned after the RQ-170 incident were designed to answer. Their answers remain classified. What can be said from open sources, from the work of researchers like Todd Humphreys, from the documented GPS anomalies in the Gulf shipping lanes, from the publicly reported program documentation of American GPS authentication research, is that the answer to each of those questions is not a simple no. It is a conditional answer that depends on the specific receiver variant, the specific operational profile, the specific countermeasures that have been applied to that specific weapon type, and the specific sophistication of the spoofing system being used against it. Iran has been investing in that sophistication for 14 years since the RQ-170 incident. American GPS authentication has been in development for the same 14 years. The question is not which side is working harder. Both are working. The question is whether the investment in authentication has kept pace with the investment in spoofing against the specific receiver architectures that are actually deployed in the field in the weapons that would be used in an actual conflict. And the answer to that question does not appear in any public document with the specificity it would need to be reassuring. Here is the final layer that every analysis of American GPS dependence underweights, because it requires thinking not about individual weapon systems, but about the doctrine that assembles those systems into a military campaign. American joint military doctrine assumes GPS works, not as a contingency assumption, as a planning constant. Mission planning for air campaigns, for ground force operations, for naval strike missions builds from the premise that GPS-guided weapons will arrive where they are aimed. The precision that GPS provides is what allows American planners to assign one weapon to one target and have confidence in the outcome. It is what allows strike packages to be sized at levels that would have been considered dangerously insufficient in the pre-GPS era. It is what allows rules of engagement that restrict the use of unguided munitions to operate without removing meaningful strike capacity. An adversary that can systematically introduce error into the GPS reference that American guided weapons use does not need to defeat those weapons individually. It needs to introduce enough doubt about whether the precision that doctrine assumes is actually present in a specific operational environment that planners must either accept degraded strike accuracy or reassign additional weapons to achieve the same probability of target destruction. Both choices have costs. Accepting degraded accuracy means accepting that some strikes miss, with all the operational and political consequences that entails. Assigning additional weapons means consuming more of the ammunition inventory that American doctrine has sized for a GPS-reliable environment, against a target set that is larger than the GPS-reliable environment supports. Neither cost is catastrophic. Neither renders American military power ineffective. But the cumulative effect of introducing that doubt across an entire theater of operations against an adversary that has invested for 14 years in understanding how to make the doubt credible is not nothing. It is a planning problem that commanders must now carry into every operational decision that a previous generation of planners made without needing to ask the question. Brian Clark of the Hudson Institute, in a 2022 assessment of electronic warfare challenges to American precision strike capability, wrote that the most strategically significant vulnerability in American precision warfare is not any single weapon system's susceptibility to a specific countermeasure. It is the doctrinal assumption that precision is a planning constant rather than a variable. An adversary that can reliably transform that constant into a variable has achieved something real, even if no American weapon is ever actually misdirected. The uncertainty is the achievement. Iran proved the variable was real on a runway in eastern Iran in 2011. It has spent 14 years since, making the variable harder to eliminate. Let us go back to the beginning. That engineer at his console. 9 years building toward one demonstration. A doctorate in signal processing. A problem that his government told him mattered more than the problem of building one more missile, one more drone, one more weapon that would end up photographed on a sanctions dossier. His problem was more fundamental. His problem was the thread. He understood something that the engineers who built the GPS-guided weapons on the other side of the Gulf understood differently. They had built their weapons around a navigational foundation that was designed for reliability, for accuracy, for global availability. They had built it with encryption and frequency agility and signal power sufficient to defeat jamming. They had built it for the threat environment they expected. They had not fully built it for a threat environment in which an adversary was not trying to cut the thread, but to hold it, and write on it, and make it say something different. He found the margin in the signal architecture. He spent 9 years learning to write on it cleanly enough that the receiver, the autopilot, the weapon, the doctrine built around the weapon could not immediately tell the difference between what the satellites were saying and what he was saying. The RQ-170 landed on his runway. The sensor payload sat on a table in front of foreign technical teams. The classified assessment was commissioned. The authentication programs were funded. The upgrades were developed. Some were deployed. The GPS constellation is still transmitting the same public signal architecture it transmitted in 2011. The guided weapons inventory has been updated in some variants, and not others. Iran is still investing in the spoofing capability that the 11 minutes validated. The authentication investment has not closed the gap with the certainty that precision strike doctrine requires it to close. And somewhere in the electromagnetic spectrum above the Persian Gulf, the same invisible thread connects American weapons to their targets. The question that 11 minutes over eastern Iran permanently placed on the table is whether, in the next operational environment, that thread is still saying what the weapon thinks it is saying. The drone landed intact. The program continued, and the engineer who spent 9 years learning to write on the thread went back to his desk and began refining the waveform for the weapon systems that would come after the drone. He has had 14 years since then to work on the problem. The thread is still there, and it is not silent.